Hello everyone. So this is part 2 of a video series on the multigrid methods for good cop Helmholtz equation. So in the previous video, we talked a little bit about the basic literature review, what are exactly Krylov solvers, and how can the multigrid method lead to such extreme speedups in our code, and why do we care about the multigrid method. And we also talked about our problem formulation. So what exactly is the good cop Helmholtz equation? How do we discretize it for this specific problem or these specific solvers? And then we talked about this method of manufactured solutions, which is this concept of choosing an exact solution for our potential u before we run the solver, and then using that exact solution to create a specific formulation of our Helmholtz equation. And then by solving that specific formulation, we expect to get back our exact solution. And this is a great method for us to test solvers' accuracy. And if we get that exact solution back, we know it's a very accurate solution. And lastly, we talked a little bit about implementation. So we're going to be using finite elements for our discretization. And then this code is all based on PETSc. So just to recap the good cop Helmholtz equation, the basic equation is this negative second derivative of u plus u equals f. And f is some function of x and y, or whatever your variables are, x, y, and z, or just x. And we determine f by plugging in our exact solution and solving for f. And then we have some boundary conditions applied to our equation. So let's look at the specifics of some of the code. So this subroutine is the create mesh subroutine. It's what builds our mesh. And the most important part of this is our dmplex create box mesh. This is the function that builds our mesh inside the dmplex object. So the dm object in PETSc is the object that manages communication between the algebraic structures, meaning our vectors and our matrices, and the mesh. It allows that communication to happen, so it's very important. So at the top, we create this mesh, and at the bottom, we set, in the middle, we're setting some options. We're allowing some options for altering our mesh, and then at the bottom, we're sort of building our dm object. So the next subroutine that's important is the setup discretization. This is essentially where we create our finite element. Right at the center, you can see, is where we're creating our finite element. And most specifically, this PETSc FE create default. This is PETSc's sort of most generic finite element creator. So we run this function to create our finite element. And the nice thing about PETSc is that we're not stuck with the options that we give here in the code. We can actually alter a lot of these options from the command line. So we can change the specific finite element type. So next we have our setup primal problem subroutine. This is essentially where we're setting our equation, where we're defining our equation. So we have two different exact solutions that we're interested in. One is a trigonometric exact solution, and one is a quadratic exact solution. Here in this function, we're setting these two different, depending on whether we have this option, this flag user trig, whether that appears or not, we set our trig exact solution, and then we set the equation. Using some other functions, this trig underscore u is a function that has our exact solution. So that we do that, and then the bottom part in the else is if we don't have that flag, we set our quadratic solution, and we define our equation based on that quadratic solution. And I'll talk about those exact solutions in a minute. And if you'd like to know more about how these residual and Jacobian functions work and what format we need for our equation, you can watch the previous video. So this is our main function. This is where we're actually running everything. So in here, we initialize our PETSc. We create our SNES object, which is our nonlinear solver in PETSc. Then we create our mesh. We process some of the options from the command lines. We set up our dm object and then our discretization. And then there's a few functions or lines that have to do with setting up our solution vector u, our potential, and then we set some more options, and then in the middle part we're basically running. SNES solve is the function that runs our solver, and then we can view some of the solutions. We get our solution, and then we actually set this option vec view from options. If you include this potential view option in your command line, you can output some image of your solution on your grid. And then lastly, we just clean up. We're just destroying some of these vectors so we can reuse them. So Here are the two exact solutions. Our quadratic solution is u is equal to 1 plus x squared plus 2y squared. And our trig solution will be sine of 2 pi x plus sine of 2 pi y. Obviously, these can be extended into 3 dimensions or pulled back into 1 dimension, whatever you'd like. But for this presentation, we're going to focus on 2 dimensions. So the next thing I want to talk about before we look at some of the results is what these multigrid cycles actually look like. And there's 2 specific ones that we're going to use in our test runs in this presentation. So the first one is a V cycle, which is the most basic type of multigrid cycle. Basically what you do, and these lines represent going from different levels of mesh refinement. And so the V cycle is basically starting at your finest mesh and then going down to your coarse mesh and then back up to your fine mesh, which is the basic multigrid cycle. And then there's an F cycle, also called a full multigrid cycle, which is where we go from the finest down to a very coarse, back up to a slightly finer, then coarse, then again a slightly finer, back down to coarse, and then finally back to our finest mesh. So those are the 2 we're going to be using in our test runs. So now let's look at some results. These are the results for the quadratic exact solution, and these are plots of the squared norm of residual and squared norm of error. So we ran 4 tests. The first test was a basic local solver, successive over-relaxation solver. Our second test was the same SOR solver, augmented with a Krylov solver, conjugate gradients. In our third test, we did an MG, a multigrid V cycle, and then lastly, we did a multigrid F cycle. And one thing to note is that some of these plots say Richardson. The Richardson iterator is sort of the most basic iterator there is. So a Richardson iterator is basically saying an SOR solver. It's interesting to note that the local SOR solver fails to reach a solution. And that's because we see this initial decrease in error and residual. And that's basically when it's solving its local problem. But as we try and solve a more global problem, the local solver needs to reach out further and further into the mesh to get more information about what's going on globally, and that takes a long time to do that. It can only do it 1 degree of freedom per iteration, which means it's going to take a long time. So you see this stagnation in our solution. And now if we augment that simply with a conjugate gradients Krylov solver, we see in the top 2 graphs that we reach a solution, and it does it much quicker than any successive over-relaxation solver can do. However, as we increase our mesh density or refinement, for this problem we used a mesh of 128 by 128, and as we increase that, the conjugate gradient solution will take significantly more and more iterations. It'll actually be asymptotically, it will grow in the amount of work it needs to do to come to this solution. So this won't work as a large problem solver. But now let's look at what happens when we apply a multigrid method to it. So in both the multigrid methods, the V cycle and F cycle, you could see we reach convergence, and we reach it within about 12 iterations, which is remarkably faster than doing our SOR, even with conjugate gradients, which takes about 200 iterations to reach convergence. So to further show the accuracy of these solvers, we can look at the final solutions that were achieved by the code. So in the top left, we have our purely local solver, and we see that it didn't even reach a final solution, and that's because we set a maximum iteration limit, being 500 iterations. If it didn't reach a solution by 500 iterations, we just shut off the code. And that's why we don't see a solution. It would take way too long to even reach a solution. So in the top right, you see our conjugate gradients local solver, and it does achieve a final solution that is converged, and it looks exactly like what we'd expect. And then the bottom 2 again are our multigrid cycles, and you can see just like conjugate gradients, we reach a solution, the solution that we expect from our exact solution. So our multigrid methods are accurate and they're fast to converge. So next, let's look at the trigonometric solutions, and they look very similar. Once again, we see that the Richardson initially has a drop in its residual and error when it's solving a local problem, but as it needs to reach out more and more globally, it just can't do it. And again, augmenting with our conjugate gradients allows us to reach a convergence within at least 200 iterations. And then if we look again at our multigrid cycles, they reach within about 12 iterations of convergence on the actual solution. So they're very much faster than our conjugate gradient methods. So once again, looking at our final solutions, we see that the local solver, the SOR solver, doesn't reach a solution within the given amount of iterations, and then the rest of our tests reach a solution that is the correct solution within the given amount of iterations. But the multigrids reached it about 10 times faster. So we've shown that our multigrid methods can be just as accurate as our traditional Krylov methods, but in far less iterations. So we've seen a remarkable speed up in our code while achieving the same level of accuracy, which is why we were so interested in something like multigrid methods. So thank you for watching the video. If you haven't already, please go watch the first video to get a better understanding of the mathematics behind this, and I'll see you in the next video.